Welcome to Lesson 2 of the series, Salesforce AI Specialist Certification Prep, tutorial. In this lesson, we will explore foundational AI concepts. If you are already familiar with these concepts, you can skip to Lesson 3, Einstein Trust Layer. You may have encountered terms like artificial intelligence, machine learning, neural networks, deep learning, generative AI, etc. in the AI context. How are they related? Artificial intelligence or AI is a broad field. Machine learning, ML, a subset of AI, enables systems to learn patterns from data and make predictions or decisions without being explicitly programmed. For example, credit card fraud detection or email spam detection. Neural networks, a subset of ML, are inspired by the human brain's structure and function. Our mind often leaps from idea to find connections between two things that are not obviously related. Some of the best insight are the result of these leaps. Similar way, neural networks make similar leaps, using nodes and layers, and connecting these nodes and layers to its neighboring ones, to figure out insight from the data. Training AI by adding extra layers, to find hidden meaning in data, is what is called deep learning. Generative AI is a prominent technique of deep learning. It uses models like Generative Pre-trained Transformers, GPT, to generate human-like content. Or Generative Adversarial Networks, GAN, for image recognition and image generation. Computer vision, speech recognition, natural language processing, or NLP, are all applications of deep learning. There are many resources available in the internet to learn further into each of these individual topics. I would encourage you to do so. Here, we will cover topics that are specific to the AI Specialist certification. Now let us look at how AI was evolved. For decades, programmers have written code that takes inputs, processes them using a set of predefined rules or algorithms, and produces an output. Let's consider the task of identifying spam emails. In traditional programming, each rule must be explicitly defined by the programmer. For example, a rule might flag emails containing phrases like free money or symbols such as multiple dollar signs. However, spammers continuously adapt their strategies, making it increasingly difficult to define rules for every new tactic. As a result, relying solely on rule-based programming becomes impractical. This leads us to an important question. What if we could train computers to learn from experience? This is where machine learning comes into play. Machine learning identifies patterns in data and uses those patterns to make predictions. In the case of spam email filtering, we provide the model with thousands of emails labeled as spam or not spam. The model processes this dataset and builds a trained model by identifying patterns within the data. Once trained, the model can analyze new emails it has never seen before and predict whether they are spam or not, based on the patterns it has already learned from the data. One shortcoming of machine learning is that we need to manually do the feature engineering. Feature engineering means identifying the relevant input and output from the raw data. Machine learning also struggled with unstructured data such as emails, chat messages, social media posts, articles, and books. Neural networks solved the feature engineering issue by learning the features automatically. It also worked well with the unstructured data. Initial neural networks has only a few layers and had a low computational efficiency. Deep learning further revolutionized neural networks, especially using convoluted neural networks, CNN, for images, and recurring neural networks, RNN, for sequences and natural language processing. With the advent of Transformer Deep Learning Model, natural language processing is improved further. Transformer architecture is the basis for generative AI. It is important to note that the rise of generative AI was significantly enabled by advancements in cloud storage, computing power, and frameworks and tools availability. Cloud platforms provided scalable storage and computational resources. Advances in computing power, particularly GPUs and TPUs, provided parallel processing capabilities needed for running neural networks. Frameworks like TensorFlow and PyTorch provided modular tools for building and training complex architectures, such as GANs and transformers. Just as humans excels in different areas, math, sports, or music, AI systems specialize in specific tasks, each tailored for a purpose. The idea of an AI, called general AI, that could do everything like a human, is still years away. Here are some examples of specialized AI systems. Numeric predictions. Examples are weather forecast or forecasting sales for next quarter. Classifications. Examples are credit card transaction, fraudulent or not, vehicle identification, is this vehicle a sedan, SUV or pickup? Robotic navigation. Examples are self-driving car or Roomba-like cleaners. Natural language processing or NLP. Examples are translation or summarization. Machine learning uses different models such as regression, classification, clustering, generative, etc., based on the tasks at hand. Let us look at an example of regression model. House price prediction. The dataset includes inputs such as square footage of the house, number of bedrooms, proximity to the city center, and the output, price. We collect a large amount of data related to house prices. The features of the dataset will be identified. Features are the relevant data elements that are applicable to the current task. Weights and biases are added to the features, based on our initial understanding of the data. The data is divided into training dataset and test dataset. Using the training dataset, the regression model finds the patterns in the data. Now this model is tested using the test dataset. For the test data, we let the model predict the output. Then, the predicted output is compared with the labeled output. If there is a difference, that is the error, or loss. The goal of the machine learning model is to reduce the loss to a minimum. The model features are adjusted by modifying the weights and biases with the goal of reducing the loss. The process is repeated until the loss is not reducing any further. There you have it. Your trained model for predicting house prices. Let us now look at some other machine learning models. Classification is another ML model. The spam email detection we looked before is an example of a classification model. The classification model groups data into different classes. Spam detection is a binary classification model, since it gives two mutually exclusive classes, spam or not. In the case of vehicle identification, the classification model groups data into multiple classes, sedan, SUV, and pickup. Classification model is a supervised model, since we use labeled data to train it. Another ML model is clustering. Clustering model is an unsupervised model that groups data points into clusters based on their similarity. For example, when a retail business wants to segment its customers based on demographics, it uses a clustering model. Next one is the generative model, which is the basis for ChatGPT, Gemini, and other LLMs. Now, we will look into generative model in detail. Let us first look at the evolution of generative AI. Google released the Transformer model in 2018. At first, the Transformer mainly impacted basic natural language processing tasks, such as translation. Once people realized that the Transformer architecture could be taken apart and applied in different ways to perform a range of tasks, its impact started growing quickly. OpenAI released its first GPT model in the November of 2022. Initially in the GPT-2 and GPT-3 models, each prompt or interaction was treated separately. Then in the later versions, memory is added. That enabled the model retains the context of the conversation. User could ask follow-up question without repeating the previous prompts. Then in addition to text, images, and audio were added. Then during 2022 to 2023, Retrieval Augmented Generation, RAG, was introduced to enable the integration of external knowledge into the LLM. The latest development in LLM, which started in 2023, is the agentic or autonomous systems. By integrating with external tools and APIs, you could perform a real-world task execution. You could send a Gmail from your LLM. A hotel front desk person could trigger an agent to finish the check-in process. And of course, you can control a robot using an agent. Now let us look at how LLMs work. A lot of information is packed into this slide. LLMs are trained on massive amounts of data, something like whole of Wikipedia or even the entire web. During training, the model creates a vocabulary from the training data. And it assigns a probability to each word or token in the vocabulary. We interact with the language model using prompts. Prompt is a set of instructions, written in such a way as to elicit the best response from the model. When we send a prompt to LLM, the prompt is converted into tokens. Tokens are the fundamental units of text that the LLM processes. A token can be as small as a single character, a whole word, or a piece of a word. The prompt "Why is the sky blue?" when converted to tokens, it will look like "Why is the sky blue?" Then it goes through embedding. Embedding is the process of converting tokens into a high-dimension vector, which encodes its semantic meaning using the vast vocabulary of the model. These embeddings capture relationship between the tokens you sent and the tokens in the vocabulary. Then it goes through the encoder part of the transformer architecture. Encoder does two things. One is self-attention, which focus on relevant part of the sentence to understand the intent. The other one is feed-forward layer, which solidifies the intention using multiple layers of the neural networks. The model already has the pre-trained knowledge. From the training, the model has learned that the sky appears blue because of the scattering of sunlight, since it has seen it many times in the training data. It has also learned that scattering, color, light are related concepts. Based on this, the model knows that the question you sent about sky and blue often relates to atmospheric scattering. Using the embedding and pre-trained knowledge, the model generates an output sequence. Now, this sequence is sent to the decoder part of the transformer architecture. What the decoder does is, it takes a sequence of tokens and output the next token. It doesn't have any understanding or knowledge about the content. One thing we need to be clear about is the basic task of an LLM is to output the next token, nothing else. It does this by picking the highest probability token at each step. Once the decoder reaches the end of sequence token, it sends out the output. Let us go through an example of how the decoder emits tokens one at a time till it gets the final result. When you send the prompt, "Why is the sky blue?" the probability of each word or token in the vocabulary gets changed. The LLM starts giving the answer, one token at a time. It starts emitting the tokens such as the sky is blue because. Let us pick up from here. Now the cumulative tokens emitted so far is the sky is blue because. See how the probabilities get changed at each step? In this step, the token molecules got the highest probability and it gets emitted. The emitted token is then added to the input. Now the new input becomes the sky is blue because molecules. In the next step, the token in got the highest probability and it gets emitted. The emitted token is then added to the input. Now the new input becomes the sky is blue because molecules in. This process repeats till it reaches EOS, the end of sequence. Then the final output is sent to you as the answer.